Okay, for our first number system conversion example, we are going to revisit our general number representation equation that we used for decimal in the previous node. And we're going to revisit that for the purpose of converting a binary number to decimal. Remember that P is our number of integer digits, and our number 11001 in binary, we have 5 integer digits. D represents the actual digit of a number in a given position, and our base in this case is 2 because we're dealing with a binary number. Position 4, or the P minus 1 position, has a 1, and so that 1 is multiplied by the base, which in this case is 2, raised to the 4th power because we are in position 4. Similarly, the position 3 bit is also a 1, or the P minus 2 bit is also a 1. So position 3 bit is a 1 multiplied by 2 raised to the 3rd power because we're in position 3. Position 2 and position 1 are both zeros, and while they're raised or multiplied by their bases raised to the appropriate power, 0 multiplied by anything is still 0. And then our rightmost digit, our least significant bit, is in position 0. So we have that 1 raised by 2 to the 0 power, which is also equal to 1. So our 11001 is 16 plus 8 plus 0 plus 0 plus 1, which ends up being 25 base 10. Remember that our general number representation equation can convert any positional number system to decimal. And as a shortcut, hopefully we've noticed that for binary anyway, we can just add the weights where the digits are 1, because when the digits are 0, the weights don't matter because 0 multiplied by anything, of course, gives 0. So to look at this shortcut with a larger number, the first step we would want to do is label the weights above the digits in the binary number. So we have a weight of 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, and 2048. Notice our weights from right to left, from the least significant to the most significant, increase in powers of 2. The next thing we need to do is we just need to add the weights where the binary digits are 1. So in this case, that would be the 0 weight, or 1, 4, 16, 64, 128, 512, 1024, and 2048. Multiplying 1 by its base raised to the appropriate power of 2 is meaningful, whereas multiplying 0 would not be, so we can disregard the zeros using this method or this shortcut. And so our binary number 11101101001 ends up being 3,797 base 10. This is actually exactly the same as the general number representation equation that we just did. And again, the subscript 10 at the end of the decimal number is used to indicate the base. Going the other direction, decimal to binary, there's 2 different methods we're going to explore. The first is a sum of weights method, which is very similar to what we've been doing. And then there's also a divide by 2 method. In sum of weights method, we have 4 steps. The first is to label columns just like we did in the previous example. But we're going to label binary weights until we get a number greater than or equal to the decimal number that we want to convert. Then, starting from the first column that can be subtracted from our decimal number and leave a positive result, we'll place a 1 in that column. And then we'll subtract that weight from our decimal number. And then we'll repeat this process until the difference of the subtraction is 0. And then in the last step, we'll place zeros in the unused weight columns. Okay, so in this first example, Let's convert 397 base 10 to binary using the sum of weights method. First step is we're going to label weights in powers of 2 until we get a number bigger than or equal to 397. So at 512 I've surpassed my 397, so I'm going to stop there. Now my second step, I have to find the leftmost column that I can subtract from 397 to still have a positive result. Obviously I can't subtract 512, but I can subtract a 256 from my 397. So I'm going to put a 1 in that column and then perform that subtraction. 397 minus 256 leaves me with 141. Now I need to repeat this process until I have a difference of 0. So from 141, I can subtract a 128, leaving me with 13. But now I can't subtract a 64 or a 32 or a 16, so the next number that I can subtract is 8. So I'll place a 1 in that column. And that leaves me with 5, so of course I can subtract a 4, which leaves me with 1. Fortunately I can't subtract the 2, but I can subtract that 1, and now I have a difference of 0. The remaining positions then are filled with zeros because those bits are not 1. Notice this is an odd number, so my least significant bit is a 1, as it will be with all odd numbers in binary. But that's a sum of weights method for converting 397 to binary. Leading zeros, such as the one in the 512 space, are optional. The divide by 2 method is another way to convert decimal to binary. Step 1, we divide the decimal digit by 2, keeping track of the quotient and the remainder, and we continue until the quotient is 0. Step 2, the last remainder is the most significant bit, and the first remainder will be our least significant bit. I'm going to use a smaller number because this can get rather tedious with larger values, but in this example we're going to convert 19 base 10 to binary. So we have a column for the quotient and the remainder, and we take 19 divided by 2 and we get 9 with a remainder of 1. So then we take our 9 and we divide by 2 again, and we get 4 with a remainder of 1. 4 divided by 2 is 2 with a remainder of 0. 2 divided by 2 is 1 with a remainder of 0. And then 1 divided by 2 is 0 with a remainder of 1. Now be careful. It is very tempting to stop at 2 divided by 2 equals 1 with a remainder of 0, but keep in mind you want to keep going until the quotient is 0. So we have to do the 1 divided by 2 equals 0 with a remainder of 1. The LSB is the top bit, or our first remainder, and our most significant bit is our last remainder, or the bottom bit. Keep in mind, again, don't stop at the 2 divided by 2 equals 1. Make sure you keep going until your quotient is 0. And also remember, when you're writing from left to right, you want the bottom or the last one is your most significant bit. A lot of times these numbers get written backwards because students start with the least significant bit and work their way down. The answer is actually 1, 0, 0, 1, 1.